So we need to finish this lecture on iterative solvers today. Whatever we leave, we have to leave this. So the world of iterative solvers, linear algebra, is a big, big world. And if you need, I was just telling Aaron earlier, if you need to master scientific computing, you need to master linear algebra. And it's the mother of all sciences, numerical sciences, okay? So last time we talked about elliptic equations and how they give rise to systems of equations that we've been dealing with. Also, implicit methods, they give rise to systems of linear equations because you get a nonlinear solver that you have to linearize and then you have to solve the linear system. But for the most part, we are dealing with we're going to give the elliptic equation as an example because that one relates to the pressure Poisson equation, okay? And typically, we represent our systems as A phi equal B, right-hand side vector, solution vector, unknown, and A is the coefficient matrix. We said that in general, the solution, that's what we learned in linear algebra, is that phi is A inverse B. And then we recognize that the role of the linear solver is to really do one or more of the following. Either find the inverse of A, which is very expensive, and I'm going to show you some plots that prove that to you, but you can prove it to yourself as well on problem 1, for example, that I gave you. Find an approximation to the inverse or solve the system without explicitly computing the inverse. We also talked about some common matrices, dense matrix, mostly non-zeros, very costly to store, upper triangular, lower triangular matrices, diagonal matrices, banded matrices, they're sparse. And we talked specifically about sparse linear systems, which show up in the vast majority of CFD applications. We said that the coefficient matrix is mostly zeros. And the idea behind sparse linear systems is that you don't have to store the entire matrix, because if you store it, it's going to be really expensive. We're going to show you some numbers now in a second. And the classic sparse matrix system we solved was a simple 1D heat diffusion problem. If you take this to 2D, you're going to get 2 more non-zero diagonals. And if you take this to 3D, you're going to have an additional 2 more for a total of 7 non-zero diagonals, okay? And now, when you think of AX equal B or A phi equal B, think of this as a linear system of equations. Don't forget that. The fact that we represent it as a matrix allows us to do amazing manipulation on the system. But in the end, this is just a system of linear equations. So if you're confused about something, just write down like 2 linear equations, x, y, and try to reason about, if you're thinking about the SOR method or a Jacobi method, write down just the two linear equations and just do the iterative solution. And then that gives you, that fixes the idea in your mind. Okay, so we said that typically we don't want to fill in, it's very hard to fill in this matrix. You don't want to do that. What we typically do is just fill in the non-zero entries. And I gave you 2 recipes to do that in Python. The first one works really well for small systems, and if you're kind of teaching basic linear algebra. And that essentially uses the function called diag that takes a vector of entries, so main diagonal, upper diagonal, or lower diagonal, and combines them, puts them in a matrix. The problem, though, is that the matrix that results from using diag is stored as a dense matrix. So all the 0 elements are also stored in the matrix, okay? Then I showed you another way of doing it using the scipy sparse module, where you do the same thing. You construct the diagonals first, diagonals of your matrix. If you know your matrix very well, you construct the diagonals, main, upper, lower, upper, upper, lower, lower, and you just put them in a sparse storage format, okay? And this is what you use, scipy.sparse.diags. You give it the diagonals, main diagonal, upper, lower in this case, and then you give it the indices of these diagonals, okay? Now, oftentimes, most of the time, you know the structure of the matrix. You have minus, for the Poisson equation, for example, or for a Laplacian in a unit square with Dirichlet conditions 0, you have -4 on the main diagonal, and then 1 on the upper, 1 on the lower, and one's on the upper diagonal, and one's on the lower diagonal. So you create those diagonals with the correct size, okay, and then you put them in the sparse matrix. Another way to do this, though, is to think, if you don't know what these entries are, ones and twos and whatever, what you do, you write down your discretization. So remember, when we discretize the Poisson equation, for example, it gives you a system of linear equations. And you just combine the coefficients on the left-hand side with the unknowns next to coefficient multiplying an unknown. And if you remember the Poisson equation in 2D, we had the central coefficient, AP, we call that AP, east coefficient, A east, A west, A north, and A south. So for a given grid point, we had 5 unknowns, right? Which was AP phi p, that's the unknown at that point, and then a relation to the neighboring values, okay? Phi east, phi west, phi north, and phi south. And those coefficients, they end up in the matrix. So for point 1, you have one equation that has AP and then A east, A north, A west, and A south, okay? So how do you do this? The way I like to do it, and many people do it this way, for unconventional matrices, you actually go and create an array of the size of the grid. So you have a 2-dimensional grid, n by nx by ny. You create an array of size nx and ny for east, south, north, west, and p coefficients. What that tells you is that for a given point, ij, you have all the coefficients for the equation at that point. Okay? And then you construct those coefficients based on, so they're all ones initially, and then the central coefficient for the Poisson equation is the sum of all of those. But then you go and set the boundary values, the boundary conditions correctly. So if you have Dirichlet conditions, you're not going to have any coefficients to the outside points. If you have Newman conditions, you may have something else. If you have some weird boundary condition, you just set the coefficients accordingly. That stage has nothing to do with linear algebra yet. This is just constructing the coefficients or the linear equations, okay? Now to combine them into a matrix, we need to turn all of these into diagonals. Now remember, AP is going to be the main diagonal, A east is going to be the first upper diagonal, and A west is going to be the first lower diagonal, and then A north is going to be nx points away, and A south is going to be minus nx points down. So all you have to do is take these matrices and flatten them by doing reshape and just getting rid of the elements that are irrelevant. So you see these 2 points here. We're going to get to an example eventually, but this is how you would do it in a complex fashion, okay? All right, so let's go to solution methods. We discussed 2 types of methods, direct methods and iterative methods. Direct methods are essentially using A inverse, or doing Gaussian elimination or LU decomposition. And I'm going to show you that they're really expensive, okay? But iterative methods are really good and cheaper for sparse matrices. So 2 benefits for sparse systems is that, 1, you don't have to store the entire matrix, and you shouldn't. And second, you have to use iterative methods. They're much cheaper than using direct methods. Let me convince you. What I have here on this slide is a comparison between a sparse and dense matrix representation for a standard Poisson equation. So del squared u equals some right-hand side. And we know that matrix has, in 1D, it has 3 non-zero diagonals. In 2D, it has 5 non-zero diagonals. And in 3D, it has 7 non-zero diagonals. Are you convinced of that? Because in 3D, you have also the top and the bottom coefficients, right? Now, the first thing you ask yourself, and that may be confusing, is if you have an n by n grid, what is the size of the coefficient matrix for a Poisson equation? N squared by n squared. Okay, why is that? So the matrix needs to be a square matrix. Okay, and then you ask yourself, how many linear equations do I have? That's the first question. For 1D, you have n linear equations because you have n points. For 2D, you have n by n, or nx by ny. So that's n squared points. Now the matrix needs to be squared, and the matrix is going to represent these n squared equations. So it needs to be n squared by n squared. That's the size of the matrix. Okay? And for 3D, you have nx, ny, nz, or n by n by n. So you have n cubed squared size for the matrix. Is this clear? So think first, How many linear equations do I have? I have one linear equation for each grid point. You just simply count the grid points, and then your matrix needs to be square, so you square that, okay? So then, for a dense matrix, for 1D, we have n squared entries in the matrix. For 2D, we have n squared by n squared, right? So n by n squared by n squared, and then n cubed by n cubed for 3D. Okay, that's the size of the matrix, or the number of entries in the matrix. Okay? Now, if we want to get rid of the zeros and just simply count the non-zero diagonals, for 1D, you only have 3n. Okay, you have only, you have only 3n non-zero entries. You have the main diagonal, and you have the upper diagonal, and then the lower diagonal. Okay? And then for 2D, you have 5 non-zero diagonals, right? You have 5 non-zero diagonals because you added east and west coefficients. So that's 5n squared. And for 3D, you have 7n cubed, approximately, give or take a few numbers, because the upper diagonal is n squared minus 1, right? And so, but this is an upper bound. Now, here are the, if you were to store a floating point number, okay, so this has n squared floating point numbers in it. And a floating point number, double precision, is 8 bytes, okay? So I'm going to give you a few examples now on doing the Poisson equation, or the Laplace equation on the unit square with different grid resolutions. For 16 grid points, a dense matrix representation requires 128 megabytes. So you're filling in 3D, you're filling in 16 cubed squared, so 16 to the power 6 times 8 bytes. That's how I got this number, okay? Versus sparse storage, 0.22 megabytes. You can actually run these numbers in Python. You can see, you can verify that for yourself in Python. For a 32 cubed grid, to store all the entries, including the zero entries, for dense matrix takes 8 gigabytes. Your Python is going to crash. Okay? It's just going to crash. It won't let you do it. But for a sparse representation, it takes 1.75 megabytes. Okay? Now you see the wisdom behind using a sparse storage. Why do we need to store the zero entries? Okay? For 64 cube, it's anyway. So now you see why this is very costly. Now, the other elephant in the room is the cost of linear solvers. So I'm going to preempt what we're going to learn today and convince you that iterative solvers are actually the way to go. And what I did here, these are numbers I ran at, I was studying them at 3 in the morning today, because my son woke me up very early. So I decided to do some work. Anyway, we're solving del squared u equal minus s with 0 Dirichlet conditions on the square, and I'm just going to put random numbers inside the square on an n by n grid. And I'm going to do a bunch of solvers. We're going to learn what these solvers are later. But this is a plot showing the time to solution versus the number of grid points in each direction. So on the x-axis, we start with, let's say, 16, 32, 100, 200, 300, 400, all the way to 512, okay? So remember, this is an n by n grid. So this is 512 squared grid points, okay? And on this first curve, I'm showing what it would cost to just fill up the n by n dense matrix. So that's n squared by n squared entries, okay? On the n squared by n squared entries on the entire matrix. We fill up the matrix and then do an A inverse. And then compute A inverse and do A inverse times S, and that gives us U. Okay? This is the cost exponential. Beyond 60, this is about 64. I couldn't even do it beyond 64 grid points. It just freezes. Okay, and then throws an error. Now the other curves, I'm showing 3 different solvers that are available to you in Python. They're all iterative solvers of some nature. The first one is the conjugate gradient. Oh, it is much better, but then it goes up. And then the other one is SP-solve. That's a standard. They call it a direct solver, but it uses what's called a multi-frontal method. So it's pretty fast, but it's It's a sparse direct solver. Think of it this way. It's available in scipy. It beats the conjugate gradient method. But then the best one is this guy in red. This is a preconditioned algebraic multi-grid conjugate gradient method. Look at that. Nearly constant cost across all grid points. So the power of using iterative solvers. Now do this over 1,000 time steps. It's gonna matter. So a solver that costs you, half a second to solve the system of equations over 1,000 iterations versus a solver that costs you, 3 seconds over here, that's gonna matter. That's gonna be a big difference, okay? And it's a big deal. Picking a good iterative solver is a big deal, okay? I hope I convinced you that we should, rather than use we should dismiss direct solvers and go to iterative solvers. Okay. Direct methods, just for accuracy of the presentation. These are slides I give in my undergraduate numerical methods. Gaussian elimination, LU factorization. You should know these from linear algebra. And then there's specifically a very fast direct solver for tridiagonal systems. So 1D diffusion equation, you get a tridiagonal system, main diagonal, upper diagonal, lower diagonal. There's a direct solver that is so fast and efficient that it's silly not to use it. Because the direct solver is going to give you an exact solution with a tolerance of infinity, 10 to the minus 16, minus infinity, essentially. Or 0, sorry, 0. So it's called the tridiagonal matrix algorithm or the Thomas algorithm. And just for, again, accuracy, I'm showing you the recipe for the tridiagonal matrix algorithm. We don't have applications for it in 2D or 3D, so we're not really going to have to worry about it. But if you're curious about how to implement it, this is the recipe to implement the Thomas algorithm. You just give it 3 diagonals: main diagonal, upper diagonal, lower diagonal, and it spits out a solution for you. Okay? Done with direct methods. Let's now move on to iterative methods. And because I was trained as a mechanical engineer, I love to start with examples, things that we can wrap our heads around and then, synthesize everything and come up with a general theory. So we said that direct methods are not appropriate for large systems of equations. Iterative methods are more appealing because they're faster, they don't cost us a lot in terms of storage, and they scale much better when we go in high-performance applications. And the idea behind iterative solvers is that we start with a guess and use a recipe to refine it. We use the SOR method. We're going to learn now how we came about to get the SOR method. Now, some of the elementary iterative methods, I'm going to apply them to this diffusion equation. I use P to strengthen the idea that this is a pressure-Poisson equation. Del squared P equals some source term. And then we discretize this guy using a central differencing scheme. Okay? We are all familiar with this. And we get this equation at every point. Now think of this. This is a linear system of equations. This is a linear equation for point ij. Okay, this is what it looks like. Minus 4pij plus I plus 1, I minus 1, etc. And then if you rearrange things, remember we are after pij, okay, at every point. The problem is that pij is coupled to all the other neighboring points. But what if you rearrange things and write pij is equal to move everything to the right and divide by 4? You get this formula. And this is the basic idea of iterative methods. We say, okay, let's assume we start with a guess for P. We know what S is. We start with a guess for P. Let's find Pij based on this guess. And then let's keep repeating. So all you do is just add an iteration index. Okay, Pij at iteration k plus 1, the new iteration, is basically the average of all the points, neighboring points, from the previous iteration. Okay? And I did this for equal spacing to simplify the number so you don't have delta x and delta x squared, delta y squared, okay? That's called the Jacobi method. Yes, of the equation. And S is known. There's no iterative value for S because unless it depends on P, it's just a known value. So to wrap your head around this, I gave you the example once. If you had 2x plus 3y equal 4 and then 7x plus 8y equals 6. For the first equation, you solve for x using the previous value of y. For the second equation, you use y, you solve for y using the previous equations of x, value of x. Now, one could say, well, as I'm solving this, I already solved for pi minus 1 and pj minus 1. Why do I use the old values? Why don't I use the most recent values? If you do this simple change, so you put k plus 1 here and k plus 1 here,